Okay, so I'd like to continue where I left off last time. And the purpose was to classify the finite mutation type cluster algebras. So let's see if this writes. It's a little wet here. So this lecture will be more on cluster algebras of surface type. And at the end, I want to talk about the classification of finite mutation type cluster algebras. Okay. So, I mean, we got a review from John's talk, but I'm going to be talking about punctured surfaces a lot. So this is actually the problem for me. This is what makes everything complicated. It's always the thing that makes things complicated. But before we do that, I want to just remind you actually how to take a triangulation and get a quiver and get a cluster algebra, okay? So let's just remind. So last time, I took a triangulation. I'll call it T, of a marked surface. So this marked surface had some collection of marked points to which I attach arcs. And to it, I associated a quiver. And once we get a quiver, we know from sort of one of my first lectures that you can get a cluster algebra. Okay, so let's see an example of this. So I'm going to take a disk with some marked points on the boundary. And this is the example we've seen several times. In it manifested itself in different ways. So so I'm going to triangulate this thing, okay? So here's a triangulation, okay? And what I want to do is get a quiver from this. So remember, to get a quiver, what I do is I want a mutable vertex for every arc that is not a boundary arc, and I want a frozen vertex for all the boundary arcs, okay? So let me just use colors so this picture doesn't get too congested. So my mutable ones are going to be red, and my frozen ones are going to be blue. Okay. And as John said, we look at all the triangles in this picture and we orient our cycles clockwise. Okay? So if we do this, the picture that we get, the quiver that we get, so I have two mutable vertices corresponding to these two. And I have all of these frozens. And as I go around this picture, I'll get a clockwise cycle for every triangle. So I have one here, I have one here, and I have one here. Okay, and I'm not drawing arrows between frozen vertices. Okay, so here's the picture I get. So for this triangle, I get this cycle. For this triangle, dropping arrows between frozen vertices. So this, and this, but I'm not drawing that one. And this guy, I get one more, like this. Okay. Just to remind you, and then from a quiver, we get a cluster algebra, and this is the A2 cluster algebra with some coefficients because of these frozen guys. Okay. So now I want to show you one more example that's a bit more complicated, just to make sure we're all on board. So here my colors are going to have a different meaning because I need too many colors. Okay. So I want to draw a torus like you do in topology, where I draw a square, but I identify the opposite sides. Okay? So I'm identifying these two, that's why I drew them in the same color. And I'm identifying these two. Okay, so I'm going to have a torus with a disk cut out. And I need a mark point on every boundary component. So there's my mark point. And this is not yet a triangulation. So let me triangulate it. So to do that, so notice, I mean, this vertex is the same as all of these vertices because I'm identifying everything. Okay? So I need two more arcs. So one arc will look like this. And another arc. Yellow is not so much different than orange. I don't know. Maybe I'll try green. Okay. So this is a triangulation. And the quiver that I get from this, so now I'll draw these vertices. Okay, so I have a mutable vertex here. And this vertex is the same as this one because I'm identifying these two sides. And I have a mutable vertex here. And again, it's the same as this one. Okay? And then I have mutable vertices for these two. So I'll call this number 3 and this number 4. And I have one frozen vertex on this boundary component. I'll call this 5. Okay, and now I play the game where I draw cycles going clockwise around all of the triangles. Okay? So let's do this. So the quiver that I get, this is vertex 2, this is vertex 1, this is vertex 3, 4, and then I have a frozen one, which I'll call 5. Okay, so what do I get here? So here I have 1 goes to 4, goes to 2, goes back to 1. 1 goes to 4, 4 goes to 2, 2 goes back to 1. Okay? And here I have 3 goes to 2, 2 goes to 1, 1 goes back to 3. Okay? 3 goes to 2, 2 goes to 1, 1 goes back to 3. Okay? And if I continue in this way, let me just, to save time, I'll just draw the rest. Okay? So you can check that this is the picture that you get. And this is what I called the dreaded torus last time. Okay, so this is the dreaded torus cluster algebra. This is a word I think that Greg Musker came up with. I'm just doing this one because I've done this with the quiver before. I told you about the quiver in the past. Okay, so everybody understand how this goes? Okay. So last time I rushed to a theorem, and the theorem I stated was not quite correct because you have to change it a little bit for punctures. Okay? So let me restate it and tell you it's true for punctures, and then I'm going to fix it when you don't have punctures. Okay? And we need these tag triangulations. Okay, so here's a theorem by Fomin-Shapiro and Thurston from 2008. So it says, so if you have a marked surface, unpunctured surface, then you have a bunch of bijections that John mentioned. Okay? So there are bijections. So the cluster variables so as I did here, okay, so if you have some triangulation, you can associate a cluster variable, a cluster algebra. So the cluster algebra is associated to the surface. Okay, it doesn't matter which triangulation you start with, you get the same cluster algebra. Okay? So this is what I mean when I write the cluster algebra here. So cluster variables of this cluster algebra are in bijection with arcs of this unpunctured surface. Okay? So let me call, if I call an arc gamma, let's call the corresponding cluster variable x sub gamma. And clusters in the cluster algebra are in bijection with triangulations of this unpunctured marked surface. Okay? So if I have a triangulation, gamma 1 through gamma n, I get a cluster for this triangulation, x gamma 1 through x gamma n. Okay? So furthermore, if I, so like in these pictures, these are all unpunctured, I can flip these arcs, or I can mutate these corresponding quivers. Okay? And that's the same operation. Okay, that's an exercise I gave you last time to show that these are the same. So furthermore, mutation at a vertex k corresponds to flipping the arc, say, gamma sub k. Okay. So last time I missed this unpunctured part, but this is important. Okay. So with the rest of my lecture, what I want to do is explain to you how can I erase this assumption for unpunctured surfaces. So to erase this, I have to write tagged arcs here and tagged triangulations here. Okay? So this is what I want to do. I want to explain to you what these more general tagged arcs and tagged triangulations are. And after that, I will talk about this finite mutation type classification. Whoa, sorry? The number of tagged arcs is this, in an ideal triangulation is the same as the number of arcs in an ideal triangulation. They have the same number. So it'll be clear more when I define what tagged arcs mean. So a tagged triangulation or a triangulation, they both have the same number of arcs in them. I'm not sure what the question is. Yeah, all triangulations have the same number of arcs. It's sort of, yeah, this tag thing is a bit artificial. It's the only reason that you add it is to deal with these self-folded triangles, these triangles that only have two sides instead of three. Okay, so let's say that. So let's recall the notion of a self-folded triangle. So a self-folded triangle is a triangle with only two distinct sides. Okay, so here's what it looks like. So say I have a triangle like this, and I'm going to stretch this triangle and stick this side to this one. Okay? So what I get is a picture that looks like this. Okay? So this side is these. Okay? And this one is the one that I stretched around. That's this one. Okay? So I'm gonna call this guy a radius of a self-folded triangle, and this one I'm going to call the loop of the self-folded triangle. Okay, so with that said, I want to remind you, last time I told you how to write quivers from triangulations But I didn't have enough time to tell you what to do when you have these, when you have these kind of self-folded triangles floating around. Okay, so I want to tell you everything in detail now. And the timer just says 1 hour and 25 minutes. Forever. So, sounds good. Okay. So I want to get a quiver from a triangulation. And my triangulation may include some of these self-folded triangles. Okay? So here's the recipe. Okay? So for any triangle, I'll denote it like this. Inside my triangulation. So I want this triangle to be not a self-folded triangle. Okay? So if I have any triangle that's non-self-folded, I get an arrow. So I get an arrow from I to j when, so I'm labeling my vertices by 1 through n, and I'm labeling my arcs from gamma 1 to gamma n. Okay? So I get an arrow from I to j if arc gamma I and arc gamma j are sides of this triangle that's non-self-folded, with gamma j coming after gamma I clockwise. Okay? Gamma j following, I'll draw a little picture. Gamma I clockwise. So this is the one we've been doing all the time. So the picture here is I have some triangle. I have arc gamma I have arc gamma j. J comes after I clockwise. This is the one we've been doing. So here's the two ones I didn't have time to get to last time. This is what happens in the presence of a self-folded triangle. So say gamma j is a radius, as defined over there, of a self-folded triangle. And I have to try to not draw the symbol for triangle here, because I don't necessarily mean that triangle. With loop gamma L, comma, and gamma I, so I'll draw a picture of this too. Gamma I and gamma L are sides of my non-self-folded triangle, with gamma L following gamma I clockwise. Okay? So here's the picture of this. So I have something that looks like this, and I have a self-folded triangle, so let's have a marked point. And I have a self-folded triangle. So I have a picture that looks like this. Okay? And just to fit everything, I'm not going to write the gammas. I'm going to write I, J, L. Okay? So here, this radius is called J. The loop, I'll call it L. And this segment from here to here is called I. Okay? So in this situation, so gamma j is a radius of this self-folded triangle. It has a loop gamma L, and gamma I and gamma L are sides of some triangle. Here's the triangle, 1, 2, 3. 3 sides. Okay, so in this situation, I'm going to have an arrow from I to j in my quiver. Okay? And there's one other case that's like this one, but it tells me sort of what to do with this boundary edge. Okay? So I'm going to write this down, but it's pretty much the same. So I'm going to skip a lot. So gamma I is a radius of a self-folded triangle, okay, with loop gamma L, same as before. And gamma L and gamma J are sides of triangle, my non-self-folded one, with gamma J following gamma L clockwise. Okay, so here's the picture of this one. So pretty much the same as before. I have some self-folded triangle. Okay, so the loop is called L. This arc from here to here is called J. And this one, this radius, I'm going to call I. So in this case, if my situation locally looks like this, I get an arrow from I to J as well. Okay? So let me do, oh, I forgot the one important thing, or one important thing, not the one important thing. So I should remove all two cycles that I may create. What's that? Can I repeat it? Okay. So it says if gamma I is a radius of a self-folded, so this means the same thing as I wrote here, if I put dashes. So gamma I is a radius of a self-folded triangle with loop gamma L, and gamma L and gamma J are sides of this non-self-folded triangle with gamma J following gamma L clockwise. Okay? So this is what the picture looks like. I have a self-folded triangle, I have a radius, and inside this triangle, gamma J follows gamma L clockwise. Okay? This means I should have an arrow from vertex I to vertex J. And the last step is remove all two cycles. Okay. So let me show you an example. Okay? So here's a marked point. Here's a marked point. I'm going to, here's a boundary component. So I'm cutting out this disk, and I'm putting a marked point on it. And I want one puncture over here. Okay? So let me show you some triangulation of this thing. So first I'll draw the sort of badly behaved part. This is a self-folded triangle. So here's a self-folded triangle. I'm going to have an arc like this, an arc like this, some arc that comes around like that, and one arc that goes here. Okay? So let me draw the quiver of this guy. So maybe I want to keep this, I may have to keep this on the board the entire time. Okay? So let's see. I'll try to draw the quiver. So let me in a different color write down these vertices just so you can match it up. So I'll call this 1. Okay? I'll call this one 2, 3, 4, 5, 6. I'm just picking this in any kind of way, it doesn't matter. And now for all of my boundary components, I want frozen vertices. Okay? So this is a boundary component. So I'll call this one 7. I'll call this one 8. And I'll call this one 9. Okay. So I'm going to quickly draw the parts of the quiver that don't involve this self-folded triangle, because we know how to do this. Okay? And then I'll spend some time on the self-folded triangle. So here's vertex 1, vertex 2, vertex 6, 3, 5, 4, and then my frozens. So 7, 8, 9. Okay, so those are all my vertices. And okay, so just to show you one of them, this 2, 2, 3, 5 gives us a triangle, a cycle. Okay, so that's this one. And I can continue doing this. So I get one like that. I get one like this. So as I said, I'm just going quick through the ones that don't involve self-folded triangle. Okay, so I've done everything that doesn't involve a self-folded triangle. So there are 2 more arrows that I need to draw in that happen to do with this one. Okay, that involve these 2 situations, B and C. Okay, so see, I have the 1, 2, 3. Okay, so this is a triangle. That's my 3 sides. And part B and part C each give me an edge. Give me an arrow. Okay? So if one of the arrows goes from 9 to 1, and one of the arrows goes from 1 to 2. So I'll draw these in a different color just to remind you that these are the ones that come from conditions B and C. Okay? So this is the picture that I get. Okay. So remember last time we had this notion of flipping an arc, where we looked at the quadrilateral that the arc was in, and we took the arc and we replaced it with a unique other arc that we could put as a diagonal inside of this quadrilateral. Okay? So I want to do this. I want to remind you that you can't do this for the radius of a self-folded triangle, so that's why we have to introduce these things called tagged triangulations. Okay? So flipping arcs in self-folded triangles so let's draw some picture. So here I have some bygone or digon, however you want to say it. Okay, there are 2 words for this. And inside of here, I have a self-folded triangle. So we saw before that it's okay for us to flip a loop. So if we try to flip this loop, there's nothing that's going to cause us any problems. So if we flip the loop, so this guy stays the same. And now we replace this with this arc. Okay? But if we try to flip this radius, there's nothing that we can replace this with. Okay? So we can't flip at the radius of a self-folded triangle. So we can flip at loops. But not at radii. Okay? So the fix is to introduce something called tagged arcs. Something called tagged arcs. Okay, so let me give you a definition of this. So the definition of a tagged arc. So last time I defined for you what an arc is. So a tagged arc is an arc with some additional bits of information. So it's an arc that also satisfies the arc should not bound a monogon, so a one-sided figure, with a single puncture. See, this condition exactly this, the condition to forbid this kind of thing. Okay, so this guy, if I remove this arc here, this guy bounds it's a one-sided figure with a puncture. Okay? So I don't want this kind of thing to happen, so I'm going to replace this guy with something that's not a loop like this, but something that has a tag. Okay, and I'll mention this in a second. B, the only endpoints, so only endpoints at punctures can be tagged. Okay? So a tagging is just some extra data I'm going to add to my arc, and I'm only allowed to add this data when my arc is attached to a puncture. And finally, so for a loop, either both ends are tagged, both ends of my arc are tagged, or both ends are untagged. Okay, so let me draw a picture for you of how we denote a tag. So we represent tags by a little bow tie. Okay? So like in this picture over here, for example, where we have this self-folded triangle, what I'm going to do is I'm going to replace this guy by a tagged arc. So if I'm talking about tagged arcs, tagged arcs don't allow this picture, as I said, because of part A. Okay? So I'm going to replace this. I'm not flipping, I'm replacing. I'm going to replace this picture. So this radius, I leave it alone. Okay, so let's call this radius r. So this radius I leave alone. And then this guy I'm going to replace with a tagged arc. So I'm putting my tag, so the information of a tag is I either put a bow tie or not a bow tie near this endpoint, or I put a bow tie or not a bow tie at the end of this endpoint. Okay, so I look at the two ends of my arc, and I either tag it or I don't. Okay? So when I have such a picture like this, I'm going to replace it with something like this. Okay? So what I'm saying is I'm writing down a map from arcs to tagged arcs. where if I'm the loop of a self-folded triangle, I replace it with this. And if I'm not the loop of a self-folded triangle, I just leave it alone. Okay? So what I'm saying is I can represent every arc by a tagged arc. Where if it's a loop of a self-folded triangle, I replace it like this. If it's not, I don't add any taggings. Okay? Some information. Oh, R. Oh, you just can't read it. Oh, I just called it R. Yeah, sorry. I didn't know if it was, I thought it was like you're asking something mathematical, but you just can't read it. Okay. Yeah, it's just, I'm just labeling, I'm saying that this is this guy. I have not changed it. Yeah, that's why I labeled it. Yep, I know it's tough to see, sorry. Okay. So any questions? This is okay? Okay. So now I want to show you one other picture. How much time do I have? Half an hour. Okay, yeah. Like if I swap them? No, it doesn't matter. Yeah, I could just, I could draw them the other way. That's okay. Yeah. Okay. So, yeah. What's that? This? So you should, yeah, this picture is kind of funny. I mean, so you should, these are my boundary arcs in my picture. Okay, so no. Yeah, so I only tag things that end at punctures. Yeah. Yeah, so I only put taggings near punctures. So really, like, this whole business of tagging is only to deal with punctures and self-folded triangles. Like I said, it's theorem, if I consider unpunctured surfaces, if I have no punctures, I'll never have these self-folded triangles. They just don't happen. These self-folded triangles only happen for punctures. And then everything works exactly like you want it to. This whole business of tags and stuff is just to make everything work, where you can flip arcs, where you can mutate. See, I can't mutate right here because of this self-folded triangle. So this tag triangulation stuff is just to deal with that. To make it where I can mutate. It's somewhat artificial, like, just to make it so I can mutate at these radii. So let me show you how you can do this. So let me try to flip now. Okay, so I said that I couldn't flip this radius before. Okay, so I'll show you now how to flip the radius. And you can imagine, so I'm going to now flip the radius. And what I get is this picture. So this one still remains. Okay, so maybe I'll draw that one in red again, just to show you that it's the same one as before. That one still remains. And now I'm replacing this one with this arc here that has a tag right there. So this is how I flip. So this is my new R. Okay, R prime. Good. Okay, so if that was unclear, let me tell you what it means for two tagged arcs to be compatible. Okay, yeah? What's that symbol? This is called a tag. This is a tag. So if my arc is tagged, that's how I'm denoting this. Okay, so this little thing is called a tag. Okay. So now I can flip at the radius of a self-folded triangle. Okay, so this was the whole point. So let me tell you what it means for two tagged arcs to be compatible. Okay, so I can tell you what a triangulation is. So maybe I can fit this here. So definition. So two tagged arcs gamma and gamma prime are compatible if, okay, so before I start, I have some notation. So the notation is going to be that if I have a tagged arc gamma, I'm going to write absolute value bars of gamma to mean take this same arc and remove its tags. Okay? Just take a tagged arc and make it plain by removing its tags. So if gamma is a tagged arc, absolute value of gamma, bars gamma, is the untagged version of the tagged arc gamma. Okay? So I have a tagged arc. I have two tagged arcs. Yep. It should, I mean, it has to be a puncture. It has, yeah? Uh-huh. Yeah, I suppose so. Yeah, so I'm going to do that. I'm going to tell you what compatible means. So let me tell you what compatible means. Okay, and it'll be the unique way to add in an arc, to remove your old arc, add in a new one, such that everything is compatible. So there will always be a unique way to do this. Okay, so two tagged arcs are compatible if their untagged versions are compatible, like I said before. So I defined compatibility for untagged arcs in the last lecture. B, if the untagged versions are not the same, okay, so I could have, like in this case, if I remove the tag from this one, then I get two of the same. Okay, so I'm saying in this condition that when I remove the tags, I don't get the same arc. Okay, that's what I'm saying. And gamma prime share an endpoint. Call it P. Then the ends of gamma and gamma prime that are connected to P, and I'll continue. I don't actually have enough space. So the ends that are connected to P must both be untagged or both be tagged. Okay, and the last condition is like this one. So if I remove the tags, I get the same arc. Okay? So if the untagged versions of my tagged arcs are the same, then at least one end of gamma must be tagged in the same way as the corresponding n of gamma prime. Okay? So this is what it means to be compatible. All right? And the definition of tag triangulation is exactly a maximal collection of pairwise compatible tagged arcs, just like before. So a tag triangulation of some marked surface is a maximal collection of pairwise compatible tagged arcs. Inside my marked surface. Okay, so I want to show you a picture. And I think this will take some time to power up. So while this powers up, let me tell you something more. Oh, okay. Okay, it's on this side. Oh, thank you, somebody. The ghosts of lecture hall. More helpful than most ghosts. Okay, great. So it powered up. Okay, so here's a picture from Fomm-Shapiro and Thurston's paper where they developed all these cluster algebras from surfaces. And so this triangle with one puncture is supposed to be the cluster algebra for D3, which is also the cluster algebra for A3. D3 and A3 are the same. Okay? I just wanted to show you this because it involves a puncture. Okay? So you can also get it from a hexagon, triangulations of a hexagon. Okay, so in this picture, this is the exchange graph, except there are no tags anywhere to be found. Okay? So I have a bunch of these self-folded triangles. Okay? And does anybody remember how many clusters there are for A3? What's that? That's cluster variables. Great. Clusters. 14. Yeah, 14. Yeah, great. So you know both numbers. That's excellent. Okay, so if you count this, do you get 14? No? Okay, so you don't get 14. I think you get 10. Okay? So I'm showing this just to show you that, I mean, you don't get everything if you don't consider tag triangulations. Okay? So this is all you get if you don't look at tag triangulations. So here's something I took from another paper by, I don't know how to say this name, Ceballos and Pilot. Yeah, Vincent Pilot. Okay, so this is a paper of theirs, and now we have tag triangulations, and I mean this is oriented a different way, but this is the A3 associahedron that I showed you before. Okay, so you just have to rotate it like this, and it's the same picture as I drew before. Okay, so I just wanted to show you this. If you include tag triangulations, now you can flip everything. Everything works nicely, and you get bijections. Okay. Cool. So now I'm allowed to fix this theorem, where I can now just write marked surface, and I want tagged arcs, and I want tagged triangulations. Okay, and mutation still corresponds to flipping, but now I'm flipping tagged arcs. Okay. And with my last few minutes, I just want to tell you, I want to state for you the classification of finite mutation type cluster algebras. Most of them come from surfaces. So, I'll leave this up and you can look at it. Okay, so I'll start over here. So recall that a quiver Q is called finite mutation type if there are finitely many quivers that I can get by applying mutations. So there are finitely many quivers mutation equivalent to it. Okay? So remember, finite type is what I classified before in my second lecture. Finite type meant that you have a finite number of cluster variables, right? And those were classified by the Dinkin quivers. Okay, if you insist on skew-symmetric, the ones that come from actual quivers, then you get the simply laced ADE quivers. And if you allow yourself to more generally look at valued quivers or skew-symmetrizable matrices, then you get all of these Dinkin A, B, C, D, E, F, and G. Okay. So I said all that to say that finite type implies finite mutation type, but the other way is not true. Okay? So here's the theorem of Felikson-Shapiro and Tumarkin from 2012. That's the year the paper was published, but it was on the archive 3 or 4 years earlier. So it says that quivers of finite mutation type so meaning the cluster algebras that I can say cluster algebras of finite mutation type, meaning the ones that come from these quivers, are, so I have 2 nodes and R many arrows in between them. Okay, so these are all the rank 2 cluster algebras. Okay, so rank 2. All right. The second category is quivers that come from surfaces, like this. Quivers arising from a triangulation of a marked surface. Okay. And then 2 more. But this is by far the most of them. So C is quivers mutation equivalent to E6, E7, or E8. Okay? Which I told you last time what those quivers were. Or 2 times ago, I guess. To an orientation of E6, E7, or E8. Okay? And lastly, quivers mutation equivalent to 1 on the last board. Sorry, I have to put this up. So Quiver's mutation equivalent to one of these. Okay? So these are affine type E Lincoln diagrams. These are extended affine type E Lincoln diagrams. And these two are some funny quivers that never appeared anywhere else, as far as I know. Okay, so they first appeared in some paper by Dirksen and Owen, where I think like these were known to be finite mutation type, but it was posed inside this paper by Fomin, Shapiro, and Thurston, where they developed all this stuff. Like classify all the finite mutation type ones. So the top 6 were known, and then later on there was a paper by Dirksen and Owen where they produced these additional 2. And then this paper by Felikson-Shapiro and Tumarkin proved that those are in fact all of them. Okay, the ones that I wrote here. Everything from A through D here. And a key element, just to mention, but I won't have time to say it, a key element in this proof is this notion of block decomposition. Okay, so inside this Fomm-Shapiro-Thurston paper, you could ask the question, I mean, I'm building all of these quivers out of triangulations of marked surfaces. You can ask the question, which quivers can you obtain from surfaces? Can you just tell me which quivers you get? Okay, and they classify this with some notion of block decomposition. So they give you some blocks, and they tell you ways to glue them, and a quiver is called block decomposable if you could build that quiver out of these blocks. And it turns out that these block decomposable quivers are exactly the ones you get from surfaces. Okay? So to prove this kind of theorem, you have to start with, to somehow take a finite mutation type quiver. You show that, I mean, they describe something called minimal finite mutation type. They showed it has a small number of vertices, and then they show that most of them you can decompose with blocks. Okay, and the rest you check by some case-by-case, some exhaustive case-by-case kind of thing. Okay? So the last thing I want to say is that I encourage you, if you are bold and want to use Keller's Quiver mutation applet, so you can try to check how many quivers are in the mutation class of these 2. Okay, it's a fun exercise. I asked you to do this for the dreaded torus already. For this one, you get 5 quivers, I think. Check me. Okay, and for this one, I think you get 2 quivers. So the way that they showed that these were different from all these is exactly knowing that there are 5 and there are 2 here. Okay? Thank you.
Excellent talk. Any questions? No questions? Okay, let's thank Jacob once again.